name's Thanom and I'm from the University of New South Wales. Today we're going to look at one of the problems from Chapter 3 on complex numbers of the Math 1131 algebra course. So we're looking at problem 60 and we're asked to sketch a variety of set of points with some conditions. So here I've set up part A and part B, and we might do a few of the other parts. So part A is asking us to sketch on the complex plane. So here's our complex plane, the imaginary axis and the real axis. We need to sketch all the points such that the modulus of z minus I is less than or equal to 2. So when we look at this modulus of z minus I, well, z minus I is actually a line segment from I to z, but if I want the modulus of that, that's the length of that, but we can just read that as the distance from I to z. So this question is asking us to sketch all the points such that the distance from I to z is less than or equal to 2, or at most 2. So if I want the distance from I to z, well, I is on the imaginary axis. And if I wanted the distance to I, from a point z to I to be 2, that would form a circle of radius 2. So if I draw a circle of radius 2 here, freehand, we'll see how we go. So if I have a circle of radius 2, that's going to go up to 3i. This is supposed to be the bottom point down here, so that looks a little bit dodgy. So this will go down to minus I. This last point out here, that would be 2 along, and this point right out here, these aren't the intercepts, it's just this edge point where the tangent's vertical. So all these points in the complex plane are distance 2. This is a distance of 2 from the point I. Now we want all the points in the complex plane where the distance is less than or equal to 2. So we actually want the closed region inside this circle. So this is what we'd call a disk. A disk of radius 2, center I, and we're including the boundary because this is a less than or equal to. So here what we have, if we were writing it, we have the set of all numbers in the complex plane, right? So all z in C, such that, with that colon, z minus I is less than or equal to 2. So that's what we have sketched there. All this, the set of points in the complex plane, so the set of these points, such that this is true. The distance from I to z is less than or equal to 2. Okay, so equal to 2 would just be a circle. And less than or equal to is the whole disk, including the boundary. Okay, moving on, we have the same condition here at the beginning, that the modulus of z minus I is less than or equal to 2, but we've also got the fact that it could be, or the argument of z minus I is between minus pi on 3 and 2 pi on 3. So when we see this argument of z minus I is the line segment from I to z. And the argument, well, that's the angle between a line parallel to the real axis, so a horizontal line, and that line segment from I to z. So here's I. Again, here's a horizontal line. Let's see if we can draw. Actually, this doesn't go right to the end. So we'll just draw a bit of a horizontal line here. So this is a line parallel to the real axis. And the angle between this line parallel to the real axis and a line segment from I to z. And we want that to be between minus pi on 3 and 2 pi on 3. So at most, we're talking pi on 3 clockwise this way, and at most 2 pi on 3, so all the way around here, anti-clockwise. So our line, I'll just use a small ruler this time, we want an angle of pi on 3 coming down this way. So I'm labeling that minus pi on 3. So pi on 3 clockwise or minus pi on 3. And 2 pi on 3 this way. Now, 2 pi on 3 and pi on 3 add up to pi. So this needs to look like a straight line here. So this is 2 pi on 3 this way. I'll just shift this I so it looks like it's in the middle. So if I want, so if Z is on this line, then the line segment from I to Z is going to make an angle of minus pi on 3 with this horizontal line here. And this is where a point Z on this line will make an angle of 2 pi on 3 with a line parallel to the real axis. Now, I have to really put an open circle here because the argument of 0 is not defined, so we can't include that point I. But remember, it wasn't equal to and equal to, it was in between these two. So if I just want the argument to be in between these two, then Z could really be anywhere in this range here. So I'm going to shade all here. And this is just the set of complex numbers which have an argument of Z minus I between minus pi on 3 and 2 pi on 3. However, that wasn't the question. The question said we wanted to sketch this or this. So we need this region as well as this region. It could be in either this or both, right? So we need to draw our circle on and shade that as well. Now it turns out if we draw our circle on, then, so let's just extend this shading here. We can be anywhere here. And the circle, you're allowed this I for the circle. So we'll have to take off that open circle there because we are allowed to put I in. And I does satisfy this requirement, so that's perfectly okay. So we're in either in this circle or our argument is between minus pi on 3 and 2 pi on 3, and we're over there. So our total answer is all of this here. They're the answers to part A and B. Moving on to part G. This one's asking us to sketch the set of points where the modulus of Z minus I is twice the modulus of Z plus I. So remember, this is the distance between a point Z and the complex number I. So let's say I is somewhere here. And that's double the distance between Z and a complex number minus I. Now, if we think about the picture, we might be able to work out a couple of points on this locus. I might just switch colours here. You see, if we want the distance to I to be double the distance to minus I, we can see that there's a point here, 2/3 of the way along, that's going to work, where this is double this. This whole distance is 2 here. So if that's 4/3 and that's 2/3, then that's going to work. So there is a point here minus 1/3 I, where its distance to I is double the distance to minus I. So we know that's a point on our sketch. We also might know there's a point down here where the distance to I is going to be double the distance to minus I. This point down here, this distance is 2. So if we went another 2 down all the way to minus 3I, we can see that the distance here is 4, and that's double the distance 2. So we can see there are 2 points on this imaginary axis that satisfy the conditions, but there are more points, and it's not so easy to see where those points are unless you've done a few of the problems. So one way we can solve this is actually to work out algebraically what's going on. So if we let Z equal x plus iy, and we substitute that into our condition here, we have the modulus of x plus iy minus I must be twice the modulus of x plus iy plus I. Okay, and we have a formula for the modulus of a complex number. Remember, this complex number is x plus I times y minus 1. Y minus 1's the imaginary part there. This is the complex number x plus let's write it in the same form, I outside of y plus 1, that's the imaginary part of that complex number. Now our formula for the modulus is just Pythagoras here. So the square root of x squared plus y minus 1 all squared, well that's twice the square root of x squared plus y plus 1 all squared. So I still can't sketch it, I don't know what this looks like, but I can simplify it until I can work out what it actually does look like. So if we square both sides and do a bit of expanding, we'll get x squared plus y squared minus 2y plus 1. Now if we square that 2, we get a 4. So just be careful, we're squaring both sides here. Let's expand the middle here. And so really we have 4y squared plus 4x squared plus 4y squared plus 8y plus 4. If we collect everything all on one side, 4x squared minus an x squared gives me 3 of them. 4y squared minus a y squared gives me 3 of those. 8y plus the 2y is going to give me 10y. And 4 minus the 1 is going to give me a 3. Still pretty ugly. Let's divide out that 3. Even though I can't do 10 divided by 3 nicely, still looks better. And you should recognize this as a circle. We've got an x squared plus, we've got to complete the square here to work out the center, but it's still a circle. So if we complete the square, just on the y squared plus 10 on 3y, that's y plus 5 on 3 squared. So that's the y squared plus the 10 on 3y. This has got another plus 25 on 9. So I've just got a minus a 25 on 9. And then we've got the plus 1 over here. Okay, so let's just make that look in normal circle form. X squared plus y plus 5 on 3 all squared equals 25 on 9 minus 1. That's 25 on 9 minus 9 on 9, that's 16 on 9, or 4 on 3 all squared, because then we can see exactly what the radius is. Okay, so this is a circle. Center is at x equals 0, y equals minus 5 on 3. Well, what's that really? That's 0 minus 5 on 3i. So that's minus 5 on 3i. That's our center. And the radius, oh, that's not how you spell circle. And the radius is going to be 4/3. Okay, so this should make sense with the points that we've already found here. Minus 5 on 3, hopefully that's in the middle of these 2 points here. That makes sense. So this is minus 9 on 3, minus 10 on 3, minus 5 on 3. So here's minus 5 on 3i. And its radius is 4/3. Well, that makes sense because that distance is 4/3 and that distance is 4/3. So what happens is it's a circle with a radius of 4/3 and a center of minus 5 on 3i. So we could pick some of the points, we couldn't pick all of the points. When you get used to these problems, you realize that these are all circles here, but algebraically we can get the equation of that circle if we need. Lastly, we have part H. So this is asking us to sketch all the points on the complex plane where the modulus of z minus I, so that's the distance from I to z, plus the distance from minus I to z equals 6. Okay, so the sum of these distances has to be 6. Now, over here, I'm improvising a bit because I couldn't find a bit of string. I have the complex plane, I've got a point I and a point minus I. Ignore this black string in the middle because that doesn't count as our 6 units. But what I've done is this measurement here, the length of string I have, joined from I to minus I, that length of string I have is 6 units long, where that's 1 unit here, right? Now, I've done that because I want, right, any point, if I have a point, any point, right, when I keep this string taut, so if I had a point over here, then this distance plus this distance is going to equal 6, and I've made the string that long. That's going to be a point that we need to sketch because that's the distance from I to a point Z plus the distance from minus I to a point Z is equal to 6. Okay, so I really want all the points, right, where that adds to 6. There's a point over here where this adds to 6. Okay, so my sketch overall is just going to be what happens when I put my pen in here and I sketch all the points, if I can. So all these points here. Just flick this around because it's not perfect here. But I need all these points. All these points I'm sketching, their distances to I and distance to minus I is equal to 6 units. Okay, so any point there is going to be 6 units. This looks quite circular. It's not quite circular though, it's an ellipse. Okay, now let's just work out these points and these points, and that can be our sketch. Okay, so at the top point here, this plus this must equal 6. So this must be 3I at the top, so that's 2 units to I, and then 4 units to minus I, gives me 6 units altogether. And this bottom point here must be minus 3I for the same reason, 2 units to minus I plus 4 units to I. Okay, now we need to work out what this point is over here. Well, whatever it is, this distance plus this distance has to equal 6, but they're equal, so they must be 3 each. I know this is 1, because that's to I and to minus I. So Pythagoras gets us that this distance here is the square root of 8, or 2 square root 2. So this point on the real axis must be 2 square root 2. This point over here must be minus 2 square root 2. So this is actually an ellipse. The foci of this ellipse are actually I and minus I, if you know those features about an ellipse. But essentially this is our sketch of all the points in the complex plane where this is true.